All right. So we are going to, well, before we start, homework due by the end of the day, right? End of the day being 5 p.m., right? That's how all the homeworks have been due, 5 p.m., right? Also, the quiz, if you wanted to take it right now, you could. Well, don't take it right now, but you could take it today, right? And it's open until Friday at midnight, all right? Everything's going to be over stress transformations, Moore's circle, right? Our little chalk like we did on Monday, all right? Any questions there? Yeah.
I had a question about one of the, I think it was the second question, when you asked to like draw, or to like sketch out some of the stress like diagrams.
Yep.
I think you used like, I can grab it real quick. But I was just wondering, how do you know with like the stress 1, stress 2, like stress 1 and 2, where those end up after you draw the stress block?
This one here?
Yeah.
The second number one? And you're asking, how do you know the direction of the stresses after you do the rotation?
Yeah.
So you follow the original point in which you plot on Moore's circle, right? So for this stress state, this stress element, right? Each one of these faces is a coordinate on Moore's circle, right? So if we go back to let's go back to this question, which is fairly similar. Well, yeah, this question's fairly similar, right? So we had, it's like the exact same thing. So we have an original stress state for an element they give us. And that original element has axes to it, right? We have a x coordinate face and a y coordinate face. You create that on that block, right? And each of these faces have coordinates that then you plot on a Moore's circle, right? So in this case, the x face, I said it had 3.8 KSI in compression, 5.7 KSI in shear stress, right? So those are my x and y coordinates. X being in compression, I'm going to sit down here, right? So I'm negative 3.5, and then that stress in shear makes my block run clockwise. Thumb pointing out of the page is positive. The positive y-axis is downward, so I'm down here at negative 3.8 and 5.7. Does that make sense?
Yeah.
Okay. So that's our x and y. So then when you start moving that point, say to find the principal stresses, right? So if I rotate, in this case, I rotated down to my sigma 1 and sigma 2, right? If I rotate clockwise, and I take my y point and move it to my principal stress 1, that means if I take this stress element and I rotate it half that, right? Half that angle, then whatever my y face was before, it's going to be my sigma 1 in this case, right? And you would find the directions of that based on the coordinates. So if we're on the right-hand side of our y-axis, we've got a positive x coordinate. That means that we have a positive normal stress, which means we have tension, right? So the force should be acting away. Similarly, on the other side, we're going to take this x point, and now we're rotating clockwise, and we're going to rotate up to here. We're going to have a negative, in this case, we have a negative normal stress, which would be compression. So that would give you directions. Then again, if you were rotating, say, other part of the question is what's the in-plane or maximum in-plane shear stress, right? So then you say, okay, I'm starting out along this line with this orientation. If I went to the maximum shear stress, I could either rotate counterclockwise and go this way, right? Or I could go clockwise and I could take my x point and rotate all the way around to that point. Okay. If we rotated counterclockwise and we took my y point and we went up to this tau max, right? When I redrew this, I would be rotating it counterclockwise, rotating it to the left, this degree, right, over 2. And then whatever that Y point was, it's now this shear stress. Does that help you out?
Yeah, I guess I'm just wondering, so like the Y and the X next to those points, that's like what faces these, right?
Yep. Yeah, this is I provide coordinates so that I can establish what faces of this element are which. Right? In this case, I'm calling this the X coordinate, the X face, and that one I'm calling the Y face.
Right, so what keeps you from like rotating it all the way around and making Y sigma 2? Why couldn't the Y coordinate be sigma 2 or sigma 1?
It could, but then your rotation angle is going to be all the way around,
Okay.
right? Be 90 degrees, because in this it's 180 degrees. So you're going to get the same answer. If that makes sense. Right? You're going to have to rotate that block 90 degrees. So now your Y face is essentially becoming your X face. Right? Because you have a 90-degree cube there, square. Does that help?
Yeah.
Okay. Any other questions? No? Okay. So we are going to finish up your review of 203, okay, eGen 203, right? This was supposed to be a review. This last example we've been working on, now we're going to try and find our shear and moment diagrams for this simply supported beam, right? Pin on one end, roller on the other, and 2-point loads acting at the mid, or not the midpoint, but along the span, right? 4 feet from one end and then 8 feet spread apart. So we drew a free body diagram, right? That's our first step. We always draw a free body diagram. We want to know unknown reactions. And then from there, we can then devise internal forces, right? Because that's really where we're headed, and that's what you did in eGen 203, was to figure out shear and moment diagrams, which are really telling us what are the forces in a member, internal forces in a member, along its length based on external forces. Right? So in this case, we calculated what our reactions were. We had, it's a terrible color, dy and ay, 8 kips, 14 kips. As I mentioned on Monday, stepping back, right? When I get to this point, I always want to think about, does this make sense, okay, from any sort of validity check, right? Gut feel that you have thinking about this. Yes, I think ay should be greater than dy. I feel pretty good about that. Sum of the forces equals 0. My statics work out. Step 2. This is where we construct our shear force diagram, right? And that's where we go back and we look at our 3 rules for calculating, or rules for our shear diagrams, right? We have the biggest of which is the fact that for any change, for any applied external force, right, we get a jump in our shear force diagram, right? So in this case, if we have a concentrated load, we get a concentrated jump. If we have a uniform load, then we have a nice smooth change or transition in our shear force diagram. It's really just the area underneath our loads. So in this case, right, using rule 1, when we have a concentrated applied load, right, AY is a concentrated applied load is our reaction, we're going to get a jump in the shear force diagram. So we're going to get a jump right out of the gate. So I'm going to draw a little line here. We're going to get a jump. Maybe we'll go all the way up to there. And we know that AY is 14 kips. So we're going to get a jump in our shear force diagram of 14 kips, right? We started at 0. Jump based on the reaction. Now we know based on our rules 1 through 3, we do not have a change in shear force, right? Because we do not have any applied loads. There's not a uniform load or anything until we get to that 12 kip load at point B. And so we're going to continue to run over until we get to part B, or point B. When we get to point B, we have this 12 kip applied load. It's acting downwards, so we get a downward jump in our shear force diagram. It's going to jump down to our 2 kips, right? 14 minus 12, is going to continue at 14 minus 12 until we get to our next external applied force, right? Whether it's a reaction or external applied force. In this case, we have a point load of 10 kips. It's acting downward where we started at 2 kips. So now we're going to get down to minus 8 kips. We're going to continue at minus 8 kips until we get to an applied force, right? Reaction or an external applied load. And we're going to bring it back to 0, right? Because that dy was 8 kips acting upward. So we're going to come right back to 0. This is another validity check on our statics, right? dy and ay. We're starting at 0. We should end at 0, right? Shear force is going to be 0. It's going to get taken out by that reaction. So that is our shear force diagram, right? Knowing now also that we have a sign convention associated with this, right? And we know that the shear force is positive. Up on the left, down on the right, right? This is positive shear. So we have positive shear until we get to point C. Right, this was C, this was B, this was A, and this was D. So we have positive shear on our member until we get to point C, and then it jumps to negative shear through the remainder of the member. Right. Step 3. Looking for points of maximum and minimum moment. Any ideas where that point might be, or points? Right, remember that the moment is the sum, right? The summation of the area underneath our shear diagram, right? So when we have positive area, we're gaining moment. When we have negative area, we're losing moment. So with that being the case, is there a point on this member where you might think that we might have a minimum or maximum moment? What's that?
Point C.
Yeah, point C, right? Because we're going to be increasing. We're going to start at 0 moment because we have no moment reaction, right, at our pin support. We're going to start at 0, and we're going to be gaining moment for every positive area that's in our shear diagram. Right? And then when we get to negative, we're going to be taking away from that. So we're going to be gaining until we get to point C, and then we're going to start losing it again, right? And in theory, we should start at 0 and we should end at 0 because we have no reactions, right? We have pin supports, so there's no moments. So I'm going to say that it's at C. So I have that in the back of my mind that there should be a transition at point C. If we jump to step 4, right? This is when we calculate our moment diagram based on our rules, right? Right? Construct our moment diagram based on rules 4 through 6. Those rules establish essentially the idea that our moment is a summation of our shear force diagram, right? Essentially the integral, which is just saying we're summing the area under a curve, okay? The rate at which we change is the magnitude of our shear force diagram, right? So if we have constant shear, then we have a constant slope in our moment diagram. If we have a linear change in shear, right, we have a quadratic slope for our shear force, or for our moment diagram. Right? They're interrelated. And if we have a jump, right, if we had a concentrated moment, the jump in our moment diagram is opposite of the sign of that moment. Right? So a positive moment, as shown there, is a negative jump. Right? Positive moment, negative jump in our moment diagram. Right? So using those rules, we can start by drawing a moment diagram. Say we got M, okay? We're going to start out at 0, right? There's no concentrated moment at the end of our member. So we start out at 0. We have no area of our shear force diagram at the very beginning, right? At the very, very, very beginning, we've got 0. So we're going to start out here at 0. We're going to increase, right? As we start out, we're going to increase in moment based on the area of our shear force diagram. Well, the magnitude of our shear force diagram is 14 kips, right? So for every foot we travel along our moment diagram, the slope of our line is going to be 14 kips, right? So for every foot, we're going to add 14 kip feet, right, of moment. So we're going to have a slope that does something like this. What's that point right there? What's the magnitude of that point at the end of that? That point B. What's that? 28. Be 14 times 2? Or no, 14 times 4, right? So it'd be twice that. 56. Right? This is 4 feet. So the area under this is that point right there, right? The area under that would be the height times the width, so 14 kips times 4 feet, or 56 kip feet, right? And the slope of that line is 14 to 1, right? We'd get 14 kips for every 1 feet we travel, right? Essentially just summing up a bunch of rectangles, right? So we're going to say we're going to jump, this would be this point, we'd get to this point, we'd get to this point, and we just continue to travel up the curve until we get to the end. The end being the point at which we change the magnitude of our shear force. If we change the magnitude of our shear force, this slope's going to change, right? The rate that we're adding moment is going to change because the magnitude of our shear force diagram changes, and that's what happens at point B. Now instead of being 14 kips, we have 2 kips. Right, so now for every foot we travel, we're going to add 2 kip feet. Okay, 2 kips times 1 foot. With that being the case, we're going to continue to add, right, until we get all the way over here. Now we know our slope is 2 to 1. We're going to add 2 kip feet for every 1 foot we travel. Knowing that this is 8 feet. Any ideas what the magnitude is out here at point C? 72, right? So it'd be 56 plus the area under our curve, or this part of our shear force diagram, right? Which is going to be 2 times 8, or 16. So it ends up being 56 plus 16, 72 kip feet. And this is our maximum moment, right? We've captured all of our positive shear force. And so we're transitioning now. We're going to take it away. And hopefully the area, our last area, is equal to our positive area and brings us back to 0, right? Because we have no moment at the end of this member. So I'm going to say that this is going to go all the way down to here. This would be 72, right? Minus 8 times 9. That's our distance to the end, was 9 feet. So this is 9 feet. 8 times 9 is 72. Well, lo and behold, we have 0 kip feet at the end of our member, right? If we wanted to know, maybe we had a critical section in our member. And we wanted to say, cut this member and say we wanted to cut, let's say, 2 feet from point C, right? There was a transition in material, transition in we wanted to connect two members together, okay? There's something going on there. We wanted to know what the internal force is at that point. We could use the method of sections too, right? If we use the method of sections, we would want to draw free body diagrams. At the cut, this is 2 feet, right? This is 8 feet, and this is 4 feet. That would be our free body diagram if we decided to cut this member at that point. If we cut that member at this point, we also know that AY was 14 kips, right? We did an overall free body diagram. We figured out a reaction at A. We decided it was 14 kips. We can then, at this point, sum forces in the Y, set it equal to 0. We have 14 minus, well, we have 12 kips and 10 kips. So minus 12 minus 10 plus V. V equals minus 8 kips. Any idea why V was positive here? What's that? Because it's the positive sign, right? Because it's up on the left, down on the right. We're on the right-hand side of a cut element. The shear force I drew was downward. Well, that's considered a positive shear, right? This guy right here, right? And we got a negative number out of it, right? Well, that negative number matches our shear force diagram at that point, right? We just calculated a point along this line, right? 2 feet from point C. Similarly, we do the same with summing the moments. All right, we can sum moments about our cut equals 0. Well, we have our reaction at A, that's 14 kips times 14 feet minus 12 times 10 minus 10 times 2 plus the moment. M equals 56. That is not right. Oh yeah, it is right. Whew. $56 kip feet. 2 feet over from point C, right? So this would be using the method of sections to figure out internal forces at any given point, right? And that's just going back to free body diagrams and eGen 203. If we just cut out a free body, right, and a body of interest, give us our known reactions, our unknowns, we can use our equations of equilibrium and figure out what our unknowns are, okay? Any questions? All right. Again, lastly, some relationships for you guys between our shear and moment diagrams. Knowing that the magnitude of our shear force diagram is the slope of our moment diagram, right? So if our shear force diagram is constant, that means we have a constant slope, right? We're being linear. If we have a linear shear force diagram, then we have a quadratic, right? So all we're doing is summing what's going on underneath the shear diagram. So if we have a linear shear diagram, we start out with a small magnitude. That means our magnitude is our slope. We start out with a small slope, right? It's almost horizontal. And then as we gain in shear force magnitude, we're going to gain in slope. We're going to start increasing in the amount of moment we have. Similarly, if we have a linearly decreasing shear diagram, we're going to have a quadratic moment diagram. Now going from a very steep slope, the fact that we have a very large magnitude of shear, down to a very shallow slope, right? We have a smaller magnitude of shear. The amount of change of moment is based on the magnitude of the shear force diagram. The moment is just the area underneath our shear force diagram. Right? Same goes on the negative side, right? It's negative shear, that's saying that it has a negative slope. We're going to be reducing our moment. All right. That was your 1.5 day review of eGen 203, because we're going to start using those principles pretty consistently when we start looking at beam bending. Right? So in chapter 8 of the text, right, it's all about beam bending. And as we have been looking at in class already, right, with axial systems and torsional systems, we're always interested in stress, right? Stress allows us to relate normal and shear stresses, allowable normal and shear stresses, right? We go back and based on the material that we select, or we can select a material based on the demands, right? Using a factor of safety to get our allowable stresses for that material, right? Based on the use of that element, right? Our ability to predict what the behavior is actually going to be. From stress, we can get strain, right? Or we can calculate strain based on change in deformation. And that strain allows us provides us a means of calculating displacements, right? Strain being a change in length over the original length, right? If we multiply that by the original length, we can get the change in displacement, right? This deflection, it allows us to look at a allowable displacement. Right? You guys ever heard of beam span ratios? Right? Whenever you design something, and whether it's in mechanical systems or structural systems like in civils, right? Civil engineering, a lot of times the code prescribes us with a minimum displacement that we have to meet, right? Or sorry, a maximum displacement we have to meet. Right? They wouldn't want, there's a big difference between strength and displacement. Something could be strong enough, but as we mentioned, it might not meet the serviceability requirements because it might turn into a trough. Right? We want roofs to actually shed water, right? So if we allowed roofs to, say, be strong enough, they could turn into pools when it rains, right? More water creates more load, creates more displacement, and start becoming a big dish, right? It starts gaining water. Well, we put limits on the amount of displacements we have in our members in order to get away from that. Vibration is another thing, right? Brick. A lot of the buildings on campus have brick facades on them, right? Those facades span over doorways and windows and things like that, and we don't want brick to break, right, or crack. And so in order to get away from that, they tell us that we can't have more than X amount of displacement. The way that they do that in the real world is they do span ratios. So they'll say, okay, if you are spanning 10 feet, right? For instance, if you were spanning 10 feet and you were supporting brick, you can't displace more than the span divided by 600, right? Or the span divided by 240, or 180, or 360. All depends on what the application is, okay? Obviously, if you have, say, a stucco ceiling or something that has very brittle characteristics, like brick, right, ceramics, you're gonna have a very tight displacement tolerance, right? A higher number that you would divide your span by. So it might be L over 600, it might be L over 100 or 1,000. Okay, it just depends. And so knowing displacements allows us to check that, right? Which is a serviceability thing. So it allows us to look at allowable displacements. Also, displacement, as we've used in axial and torsional system, right? Deflection provides equations for solving unknowns. What the hell just happened? Okay, we're good, we're back. So we get to provide equations for solving unknowns. Right? Like with axial and torsional systems, if we had more unknowns than we had equations of equilibrium for, we use compatibility, or the sense that something might displace, and if something displaces, something else is going to displace relative to that. We came up with some relationships that combined what the displacements were in a system, and then we had equations for the displacement based on forces and geometry, and we could relate those two together based on forces, and gives us another equation of equilibrium, essentially, right? Another equation to use to solve unknowns. So that's where we're headed, okay? So, for you METs, right? Car hoist, right? 4-post car hoist. This probably is one that sits up in, well, I designed one time this garage in the Yellowstone Club. And it's like a 5-bay garage built into the side of a mountain. And it was for the owner wanted to store all of his vehicles. And on top of that, he had so many vehicles, he had more than 5. So we ended up putting in car hoists so that he could pull in, hoist it up, and then park another vehicle underneath it, right? And so if you had that problem, right, and you had to do that, and you started stacking cars on each other, right? So we might have a beam, right, that spans between posts, and that beam has point loads on it coming from our tires, right? So we have tires that are sitting on this beam. It might look something like this. That beam might span simply supported from one column to the next. And then we have our car load P, right? So for instance, we had a pretty heavy car. We decided we're going to do 2 kips. That was just part of that person's house. They had an underground bowling alley underneath their driveway. Like full, like, oh my God, it was ridiculous. They had like a window package that came from Sweden or something like that, which was like, it was almost $200,000 for just these windows that were so that they could like accordion out and basically a large portion of the house could open up so they could have Lone Peak out there, you know? So maybe some of you someday think of me, right? Think of me. Remember to pay it back. All right, so if we had a car, say it weighed 8,000 pounds, so it's definitely not this car right here, right? It might be a 1-ton pickup, okay? 8,000 pounds. We're gonna have two kips at each one of our 4 tires. We're gonna put these 2 tires on our beam. Based on symmetry, I think we could all agree that we are going to end up with 2 kips of reaction at each side if we did some of the forces, some of the moments, right? Based on that, our shear force diagram would look something like this, right? Reaction, we bump up from 0, move over 2 kips, till we get to another reaction, another external applied force, 2 kips downward, boom, bumps us down to 0. We have 0 shear force in our member until we get over to point C, then we jump back down to negative P, or negative 2 kips in our example here. And then we get to the reaction, and it's going to bump us back up to 0, right? So we started at 0. We're going to end at 0. Okay? That's our shear force diagram. Again, we're interested in moments, right? Internal forces along the length of this member. We're going to start at 0. It's simply supported. We start at a pin. We're going to increase at a rate, right? The rate is going to be equal to the magnitude of our shear force diagram. In this case, it's 2 kips. For every foot we move across, we're going to have 2 kips. Ooh, is that what I did? I did that. That's all right. We're gonna go to metric here. I'm gonna change all these to kilonewtons because I don't know why Tim decided to do this, but he did. Tim being me, right? 2.5 meters, 5 meters, 2.5 meters. I'm gonna change this for next semester. That's stupid. Metric is stupid, right? Except for I have had to do it. So that's why I leave it in this class to some level, because I have had to deal with stuff in metric units, okay? It was not in this country, but who's to say you guys won't be working in this country either, right? So, moment, right, is the area underneath our shear diagram. In this case, we had 2 kilonewtons of shear force. It's acting over 2.5 meters. So that point at the end of our little curve there is going to be 2 kilonewtons times 2.5, or the area under our shear curve. We get 5 kilonewton meters. Our shear diagram goes to 0. Right? We do not add or subtract any moment, right? So we're just going to have a constant moment. So we get to the other end. This area obviously is the same as this area, so we're going to close this out. We're going to go back to 0. That's what I'd expect. There's 0 moment on the end of this member. If I was designing this car lift system, right, I want to know what stresses are, right? I'd be asking myself, what is the maximum stress at top and bottom? We'll talk about why that is, of this member. Right? I really just want to know what the maximum stress is. I need to know the maximum stress because I'm going to relate that back to material properties. And I'm going to select what type of steel I use for this car hoist system. Okay? Surprised we didn't make it out of gold or something. Right? So how do we do that? Right? Well, ultimately, right, we want stresses, but as I mentioned before, deflections are a critical part of bending, right? Allows us additional equations, allows us to relate back to allowable displacements, and it gives us more equations, right? So what do we know so far? Well, if we step back to previous chapters and we look at axial systems, right, axial members, we had displacement equals FL over AE, right? Which was the same as saying stress times length over E, right? All of this came from the idea that we have stress equals E epsilon, right? All came from Hooke's law. We knew that we knew the change in displacement, or delta, over the original length. That's epsilon times E was stress. So we just rearranged the equation. We then had an equation for stress, which was just the force over the area. If we did torsion, we have T L over J G. Similar concept, we use the Hooke's law version for shear. And what are these? Well, it gave us, right, deflection. Well, that's not, gave us deflection or, sorry, phi, which was twist. As a function of stress, geometry, and our modulus of elasticity, right? Material properties. Well, beams follow the same principles. But our internal forces are more complicated. Right? We did axial loads. Axial loads just created normal stresses, right? Torsional loads just created shear stresses. Well, beams create both. Okay, we're going to have moments. Moments are going to create normal stresses. We're going to have shear. Shear is going to create shear stresses. Right? So where do we start for beams? We start where, what forces act on or within the beam, right? We need to know forces. Forces will then allow us to get stresses. These forces are our shear and moments, right, that we've just devised. You guys have done in 203. We get those forces with our trusty friend, the free body diagram, right? Always drawn free body diagrams. That allows us to figure out external reactions, internal forces. Free body diagrams. From there, once we have forces, now we can figure out what stresses exist in the beam. And this is really our current focus, because you guys know how to do step one, right? Figure out those internal forces or external applied forces based on devising a free body diagram. Right? Well, to find stresses, we need external forces. We need to know now how those internal forces, or how the internal transmission of forces, go from force to stress, right? So for, like I mentioned, when we looked at axial, it was uniform, right? We had uniform stress, and axial force created a uniform stress. When we looked at torsion, we had our circle. Right, we had this behavior going on where if we provided a torque on this shaft, right, we were going to be putting a shear stress on it with the greatest magnitude at the outside face, which is our maximum diameter or maximum radius, right? And it goes to 0 at the centroid. So we had this linear varying stress. So we need to know how that stress transmits across the cross-section with our bending forces. And finally, we need to know the geometry of the member. Right. Geometry of the member is going to allow us to calculate what those force magnitudes are. Right. How are we doing on time? Okay. So step one, understanding our external forces. Right? What if we had our example that we just had, right? 2 kilonewtons. 2 kilonewtons. We know that this was 5 kilonewton meters. These were all 2 kilonewtons. 2 kilonewtons. So on, right? If we looked at a small sliver, small little section of this beam, right, we're going to say from H, H to K, K, we're going to cut it twice. We're going to put 2 cuts in it. We're going to draw a free body diagram of that little piece. That little piece is tiny. It'd be like the tiniest little sliver of this beam, right? Delta X. So we take this delta X. And we draw that delta X out here. Blowing it up. It looks something like this, right? H to H, K to K, to delta X long. Right. If we're drawing a free body diagram, this thing has forces on it. Well, that's why we went through and we calculated our internal forces, right? Or a shear diagram and our moment diagram that gives us our forces acting at any point along this beam. Well, at point H, H, K, K, that little differential segment, right? That small little segment of beam, we've got 0 shear force, okay? That means we got 0 forces acting up and down on each one of these faces. And then we have a moment of 5 kilonewton meters. It's positive. When we know a positive moment, sign convention, makes this section smile, right? 5 kilonewton meters. 5 kilonewton meters. And that's going to be our little free body diagram for this section. That moment that's applied to this member creates normal stresses on the faces. Moment. Right? A moment is a force at a moment arm, right? So when we put a moment on the ends of this member, what we're really doing is we're applying a force, right? Force at a moment arm along the cross section of this member. So if we look at that again, we redraw this. Nice little square. We've got H, H, and K, K. As long as you have some sort of axis, we're going to call this the neutral axis. Okay. If we look at our positive moment, right, 5 kilonewton meters. As I mentioned, that moment results in normal forces, right? A moment is just a force at a moment arm. So what's going on the other side? Well, we've got a force. We'll do this. So we can take that 5 kilonewton meter moment, right? It's the same as a force acting at some moment arm, right? And that force acting at some moment arm, those FC and FT create a couple and it's trying to rotate it. It's trying to rotate it in the same direction as our moment that we applied at KK before, right? Well, we'll find that this force creates stress. A linearly changing stress. We're going to derive that on Friday. Good time to blow your mind right before a weekend. All right. So with that, we'll continue this on Friday. Don't forget the homework is due today. Don't forget that the quiz is due by Friday.